Jnanam paramam dhyayam. Knowledge is supreme.
After these practice problems on polymatrices, we now move on to problems on charged particle in an electromagnetic field whose Hamiltonian is given to us, and the Hamiltonian is given by, this is the Hamiltonian. So, a general representation of the Hamiltonian for a free particle we have seen is p square upon 2m, and here we have a particle which is charged in an electromagnetic field and its Hamiltonian is p minus Ea, okay, plus the scalar field phi. So, where A is the vector potential and this phi is the scalar potential which is given to you, and p is a momentum. So, now we have to find out a quantum mechanical Lorentz force which is proportional to the d square r by dt square. So, you know classically how one writes the Lorentz force, you have to derive the quantum mechanical version of it. So, let us start by writing the d by dt is equal to minus I h cross. Recollect this, we have been using several times, time evolution operator. So, this is the Ehrenfest theorem which you are going to write for x, which is the position operator or the position which has no explicit time dependence. So, we just have dx by dt is equal to I upon minus I upon h cross and the commutator of x with the Hamiltonian. We will not have the second term in this because x do not explicitly depend on time. So, we can evaluate this by substituting h over here, which is you can write this in terms of the 3 direction px, py and pz. So, when I write this, what do I get? I h cross x, I will have a 2m which I can take outside, okay. And when I operate, when I use this Hamiltonian operator, okay, and try to evaluate this px, py and pz, I can write separately. So, I will have px minus Ea square, okay, plus I will have a py term plus pz term, right. So, I can take a commutator of just this term and the remaining term py minus Ea, this is x, this will be y, okay, sorry. So, this will be a plus the same way we used to write for p square, operator p square, how we wrote it as? We wrote it as px square plus py square plus pz square, correct. So, here only this term will contribute, that is why I am writing here this term, and the remaining term would not contribute. So, these would not commute, I mean these would give 0, they will commute, sorry, and this will give you a non-zero result. So, I can just take this term px term and the commutator of E phi with x will also be 0. So, only contribution comes from this in the through the entire Hamiltonian. So, let us drop this term minus I upon 2m, commutator of this we know x p square was 2 px. So, similarly, I will have a h cross I h cross times I will have 2 p x minus E A x, which is a function of r and t, that is A is a function of x, y, z and t, okay. So, this is what I have. So, finally, dx by dt will be nothing but px minus EAX r comma t. Here I will have a factor of just this will be 1, this will be 2, so 1 by m. Okay. So, next step would be to calculate V dV by dt. Okay. Now, we know this is the simple definition of V velocity will be dr by dt. So, dr by dt will give me V, and this dr by dt, now this was for dx, right. So, if I do it for dr, I will have p minus E A, correct. So, this will be nothing but this for the velocity. Now, there will be a time dependence which I can write it as p minus E A r comma t, correct. This is what I obtain for velocity. Now, you know velocity, in terms of velocity you can rewrite the Hamiltonian. So, your Hamiltonian was, there is a square which I missed, sorry. So, Hamiltonian is 1 by 2 m p minus E A square plus E phi. So, this I can rewrite as V square. So, half m, there will be a m square, okay, coming from here. So, this will become in terms of p, so there will be m square V square times this will be replaced. So, I can rewrite the Hamiltonian operator as half m V square plus this term will remain unaltered. This is also a function of r and t, which I have not written here, but it explicitly it means that it is a function of r and t. Here also it is a function of r and t, the coordinates, space and time coordinates. So, now in order to calculate dV, so let us do it for x. Now, velocity is time dependent. So, we will have this modified as minus I h cross, then I have Vx h plus the partial differentiation with respect to t. So, this is what I have. For this you just look carefully here, you have to evaluate few things. So, that is V of x and V square. This means you have to evaluate what is Vx, Vy and what is Vx, Vz. Vx will not contribute. Okay. So, this you can write it as V square, this can be written as Vx square plus Vy square plus Vz square, correct. That means you have to evaluate Vy square and Vz square. So, that means you have to evaluate this. So, going in the doing back engineering, that is going from the bottom to the top to get the result, let us evaluate what is Vx, Vy. Okay. So, Vx, Vy you will substitute for V, that is 1 by m Px e raised E Ax, similarly for Vy. So, you will have 4 terms. So, the 4 terms would be, let me write 1 by m square, it will become, I have P x minus E, so there will not be a vector, A x, this is the first term commuting with Py minus EAy, correct. So, this is what we have. Now, commutator of Px and Py is 0, they commute, and Ax, Ay they will also commute. So, you will be left with the commutator of Px with Ay and Ax with Py. When you do this, what you obtain after doing all the substitution and everything, you will obtain I h cross, there will be a E upon m square c, that is what you will obtain by doing all the substitution. Okay. Times you will have Bz. Bz is nothing but, how will I write Bz? it will be d, so z, so x and y, dou x a y minus dou y a x, it will be in this form. Okay. So, this b z is proportional to this. I mean, we have got it from here. We wrote b z in terms of a and in terms of b. Okay. So, this is what you have when you do the when you solve this. So, you will have 4 terms, again I am repeating, only the cross terms, these two will contribute, this and this and this will give me p x. So, this is p x a y, here I will have p y a x, this will give me term proportional to b z, okay, z component of magnetic field. So, similarly you can write what will be V x V y square. V x V y square is simple, you can rewrite this and use the relation V x, this one, V y, I will have square, I can write here V y plus V x V y V y. This is a standard way of solving. So, I h cross E upon m square C, this we have already. Okay. This was this is nothing but, okay, I wrote this beforehand only, sorry. This will be written as V y V x plus commutator of V x with the V y on the left, commutator of V x V y with V y on the right. So, after substitution you get B z. So, V y B z, this will give me B z plus B z V y. Okay. This is what you obtain on substitution. Similarly, now you can guess what will be V x V z square. No need to repeat this exercise, you can just make a guess. So, everywhere when you have x and y square, you will have V y B z. So, now I will have V z B y, correct, or V y B z. So, here I have z, right. So, now here I have z. So, now here I will have y, B y V z. Okay. So, this will give me V y B z and this will give me B z V y, correct. Similarly, you will have a swapped term. Okay. So, here I have got this contribution. Okay. There will be a minus sign here because here you have V x V z. So, when you are doing this, be careful with the sign x y y z z x. So, here it has to be z x to have a plus sign, but I have x z. So, I will have a minus sign. So, now going further, you have to add these two to get V x V square. Okay. When you do this addition, you will simply obtain V x by dt is nothing but E by 2 m c V cross B x component plus B cross V x component plus E of E by m. Okay. So, just let us go back here. So, here we had this, we have to find out V x V square, and V x V square we had broken in steps, wherein here we obtain V x square plus V y square plus V z square, we add these two. So, here we have V y B z minus V z B y. So, this will be V cross B term, one V cross B term will give me V x x term v cross b x and b cross v x. So, we have resolved this part. In the second part, and that is the second term, what we have done is dou by dou v x by dt. You can just rewrite this in terms of phi e in terms of phi and obtain this. This is nothing but quantum mechanical Lorentz force, okay, in x direction. This is for x direction. Now, in general you have, what you can do is, when I rewrite in general, I will have, so this will be again x component, okay, remember. So, when I have to find out in general, dv by dt will be E upon 2 m c v cross b, okay, minus v cross v, this is the term, plus E by m. So, this is nothing but the quantum mechanical Lorentz force, which is proportional to this dv by dt. You can rewrite this, this is nothing but d square r by dt square, which is asked in the question. So, it is proportional to this in terms of the quantum mechanical Lorentz force, and I think this part was also discussed in the lecture. So, it will help you to understand better if you try your hands on and do the exercise by yourself, which I have been telling in all my tutorials, but it is very helpful when you do it yourself at least once. And the fifth problem, after the exercise of commutator bracket for and the poly spin matrices, which was there in the previous tutorial, fifth tutorial you will find as very simple one. So, in this you have S square, you have to prove that S square Sz commutes. Okay. Okay, if what will happen if S square and Sz commutes? If S square and Sz commutes, then they form simultaneous eigen kit. You have also seen the same thing for angular momentum operator. L square Lz is commuting, so you can form a simultaneous eigen kit for L square and Lz. Lz and here Sz form has a diagonal, is a diagonal matrix. So, it is easy to calculate the eigenvalues in eigenvector, and once we know the eigenvector of Sz, we can have simultaneous eigen kit for S square also. So, the eigenvectors of Sz will also be the eigenvector of S square, and that simplifies to, the calculation. So, let us start by doing Sz. You can write it as Sx square plus Sy square plus Sz square, correct. You have to find the commutator of Sx square with Sz. Okay. So, you have seen already, and in general also you have Sij, Si, Sj. You can write it as, remember, just recollect that S operator, spin operator, can be written in terms of polymatrices, which we have discussed already, or you might have seen in the class at least once. So, in terms of polymatrices, you know what is the commutator of sigma I, sigma j, which we discussed last time. So, this will be h cross square by 4, correct, sigma I, sigma j. And what is sigma I, sigma j? If I write in terms of epsilon I, j, k, sigma k. Okay. So, when I and j are equal, this will be 0. You all know this tensorial notation. So, using this, with the help of this, you can actually calculate what is S square Sz, right. S square Sz will be sigma x square sigma z, which will give me what it will give me, sigma upon, this will give me, and so the same relation actually you can rewrite this again. I will just come here back to this, you can rewrite again as this relation. So, either you substitute for this and check the result, or you keep these in terms of Sz notation if you know the commutator of S. So, if I substitute for this, I will have, I can rewrite this as, I will have sigma S sigma x, so I will have a y, so minus y minus sigma, this will be y sigma z. So, when I am rewriting this, I will have the form minus Sx Sy minus Sy Sx. And what do I obtain for Sy square, Sz square, Sz? It will be, now you have a y z. So, you will obtain Sx Sy plus Sy Sx, and for Sz square Sz, you know the commutator is 0. So, when you add these, what you obtain, the final answer as commutator of S square with Sz is 0. This is an important result, and this result means that S square and S form a simultaneous eigen kit. So, eigenvalues of Sz and eigenvectors of Sz can help you to find out the eigenvectors of S square. So, in the second part, you are asked that show that the eigenvectors basis of Sz diagonalizes S square, and you have to find the eigenvalues of S square also. So, B part, now you can write Sx in terms of polymatrices. We have seen that H cross square 0 1 0 1 0, correct, Sy H cross square 0 minus I 0, and Hz is H cross square 1 0 0 minus 1. See, Sz is a diagonal matrix. So, you can see from here, you can infer from here that it will have eigenvalues 1 and minus 1, and the eigenvector will be of the form plus and minus kit, right. So, these will be the eigenvectors or eigenkits, and eigenvalues will be plus and minus 1. It is very simple to infer from this. Now, you need not use the eigenvalue equation, you are very much familiar, and just by looking at the matrix, if it is diagonal, the diagonal elements would correspond to the eigenvalues, and eigenvectors you can easily write them in terms of plus and minus kit, plus kit, minus kit. For 2 dimensional or 3 dimensional, you write in terms of plus, minus and kit 0. So, this we know already. So, now S square will be, S square, how will you calculate? It will be H cross square upon 2 Sx square plus Sy square plus Sz square, correct. So, if I make this substitution in terms of sigma matrices, what do I obtain is, so here I will have to write sigma x, sigma y and sigma z, because I wrote already the H cross square upon 4. So, when I square this square plus this square plus this square, we know that sigma I square is 1. So, this will give me 3 h cross square by 4. It will be identity plus identity plus identity, which is nothing but identity matrix. Okay. So, this identity matrix would give me, now this, when you operate an eigen kit plus on this, what do you obtain? When I operate s square plus state, if I operate on this, what do I obtain is 3 h cross square upon 4, and if you have an identity operator, when you operate a plus, it will project out the, it will just give me 1 and it will project out the plus component, which will be nothing but 3 h cross square by 4 plus. Okay. There in some places you will find that this plus kit is represented as plus half and minus kit is represented as minus half. So, this notation wise, I mean here the same thing as what here you have, that is when you write the eigenvectors as vectors as 1 0 or 0 minus 1, they would correspond to plus half and minus half. This you should remember. So, this is called as spin up state, this is called as spin down state. These things you must remember. S square when operated on minus kit, this will give you 3 h cross square by 4 and minus, this is nothing but down state. So, it will project out only the down state when you operate this on. You can work out each step if you are not very much convinced with what I have written here. So, from this you can see, or you can also think in another way, like s square when operated on these eigenvector gives me the eigenvalue of the form s into s plus 1. So, this forms a simultaneous eigen kit, but it gives you the eigenvalue. So, this will be the eigenvalue of the operator s square when operated on the eigenstates of Sz, the eigenstates which we have inferred from here, plus up and down state. So, when you substitute for S as half, what do you obtain? You get the eigenvalue S into S plus 1 h cross square, actually h cross, okay, square root of S into h. So, when you do S square, you will have S into S plus 1 h cross square. So, the eigenvalue of S square will correspond to S is half plus half. So, this will be 3 by 4 h cross square. This you remember, this is the same result as we got for orbital angular momentum, which was L into L plus 1 h cross, square root of L into L plus 1 h cross for L. So, L square, it was square of this, square of this. Okay. So, with this we can end here, and there will be more problems which we will discuss in the later tutorial, but I hope you must try your hands on each and every problem to ease yourself with the assignments. The assignment problems would be objective maybe, but they would give you, there will be a better chance to understand the assignment and get all your problems right if you are going in hand with the tutorial and the lectures.